So I have a question that was asked earlier as a question for the panel, and I think as maybe speaking with synopsis, it's what do we need first? Do we need more power in our tools, more resources, more compute power, or do we need more thinking power? Do we need more efficient human beings or more efficient machines? Yeah, anyone, whoever wants to take it first.
Yeah, the background of this question, I raised it at lunchtime when we had a quick chat, is do we need more compute power or more engineering brain power? So what is idling more during the verification process? And I heard Nick's answer so far, perhaps.
Okay, I think, Okay, see, I have a different view as all of you because I'm representing Doulos. That means we are on the educational side, and I would say what is more important is really to improve, say, creativity and not, say, on the first line, say, the power of computers and machines.
Well, I think we need a smarter verification. Let's think about detecting finite state machine deadlocks and that kind of stuff, which is all corner cases in the traditional verification methods. I think we need something beyond doing some kind of assertion-based verification, automated CDC verification. It means everything which goes beyond the traditional method of SDA, simulation, maybe checking.
Well, at the risk of saying they're both important, and therefore, as JL would say, then neither is important, I guess I'm not quite ready to say that only one is sufficient. Maybe both are necessary. As we saw earlier in the automotive industry, that they showed that faster horses was not enough and not sufficient. And imagine where we'd be today if we focused on speed and capacity only and not on intelligence or on smartness. But yet a lot of people still ride horses today, and the faster they can go, the better. So why not take advantage of all of the compute processing and compute power that our customers are designing and building, and run our tools as fast as we can, take advantage of all of that, but at the same time take advantage of development in technology and methodologies to be able to do things just smarter overall.
Okay, so on the one hand, of course, what everybody would want to have is the more capacity tools, the more compute power, right? Of course, it's one of the things we are also exploring at OneSpin with going to the cloud, so giving you a chance to scale stuff, a lot of stuff in parallel. But of course, this is never going to be the answer for everything. So you will need also to really use your brain and really figure out exactly what you want to do and where to apply this, because it will never be able to answer everything.
So are we everyone answering the question? You've given some good answers, and I guess if I have to answer the question being at the end of the line, I will change the topic slightly. I read a very interesting book recently, actually on the plane. I've been on the plane a lot, talking about, it's called The Innovator's Solution, and it's a great book if you have a chance. One of the things it talks about is disruptive versus sustaining technologies, and how different cycles in an industry may go from sort of a vertical tool-based, a vertical solution-based to a standards-based. And maybe separate from this, maybe it's interesting to consider whether we're in a state, if we're going to a lot of standards-based, and whether we may eventually swing back to the case where we need to have a more integrated solution, because the solutions that we have today, maybe now they're solving our problems, we just need more performance, but maybe we eventually have tools that they're good but not good enough, and so we need to have a different model besides the standards-based. So again, nothing to do with the actual question, but I think it's interesting, so thank you.
Okay. First one.
Yeah, so we had a speech saying that we one day, all on the informal, are we saying that? Do you share this? And we also had another presentation showing how to debug hardware, software, co-environment, what this relates to formal. I mean, is it possible to go straight one day doing only formal,
and is formal going to share to cross the boundary hardware software.
Yeah, that's nice. Of course, this is something also not only we are looking at, also the software border for the system software. It's nothing that is kind of ready off the shelf and nice to use at the moment. Will it ever get there? It will definitely get a lot closer to that. Of that, I'm convinced. Are we going to get there that everything runs in formal? That's maybe a little bit too optimistic.
Well, I think that where it's possible to use formal, we always should. And as we saw earlier, it's that the technology has come a long way over the past few years, and we expect that it will continue to develop as well. At the moment, today, as long as I'm quoting old Americans or whatnot, as Mark Twain would say, the news of my death is slightly premature in terms of simulation. Simulation continues to grow as well. Of course, it's not growing as fast as formal, not growing as fast as emulation, but it's still a predominantly acceptable technology, and there are still some things that simulation can do that it's very well suited for. On the other hand, we're continuing to develop, all of us are continuing to develop formal technology as well in terms of capacity and application. And so wherever it is possible to automate, I think we're continuing to do so.
But I think it's a very powerful stuff, formal verification, but I don't think it will be able to replace traditional methods, especially in the timing area. Formal has no clue about timing. So I think both methods have the right to live, but I think formal is a powerful add-on where you can find out stuff you would only find with traditional methods using a lot of effort.
Okay, yes, I believe that formal might have, say, the biggest growth now, or starting now, or up more than simulation has, but I believe there's still, say, a big need for simulation, especially also, say, with respect to hardware-software co-verification, what we did 10, 12 years ago extensively already. But I don't believe that we can skip this totally.
Well, okay, it's all about do the right things right. So formal may be one thing that should be done right, but it may not be the ultimate solution. There are plenty of tools out there are plenty of methodologies out there, so it may even be that from project to project, the flow may vary, the design flow may vary a bit, the composition of methodologies may vary a bit. So I think we heard the word smarter from Robert here. We heard from JL in his speech a couple of minutes ago that you may have not sufficient time to do everything that you would like to. So be smart and decide on the methodology, components, and the tools that you use. Choose the right ones, rethink it every time, challenge yourself, and well, the tools are there. Just select the right ones.
So, I did not say that formal will do everything. What I did say is that formal will dominate. And I did not predict when. But I think if you look at the trends, I would say it's inevitable. What's inevitable here is that simulation is growing at 6 to 5% a year, depending on the year. On the average, over the last 5-6 years, it's about 5%. And formal, depending on the branch, whether it's property verification or equivalency, which are becoming merged, by the way, now, not just by us, but by other vendors, is growing well over 30%, 35, 25, 30, 40%. So it's inevitable. But the market size is very different. So this is going to take a while before economically you can stand up here and say formal has arrived economically from a dollar perspective to where it is dominating simulation. That will take a long time. What I think is important is to realize a few things. One, it's not going to be possible to use brute force, which simulation is brute force, smartly going into the future, no matter what type of computers you have, and no matter how much wattage you can put. into those farms. The message that I think I'd like to leave people with is formal is going to grow, and it's not just Jasper formal, but formal in general is going to grow in capacity, in reach, in application, and in capability. If you're smart, get knowledgeable with formal now so that your career as a verification engineer 10 years from now and 15 years from now is not derailed and you're a dinosaur. Become aware of it today. Become knowledgeable about it today. It's, knowing about ISP prime today is not useful. You need to know about UVM, you need to know about system Verilog test bench and so forth. Get acquainted with the technology that's going to be dominating the future today. And there are plenty of choices. Obviously, I know what I think about the choices, but you can make your own choices.
Did you want to say anything? Okay.
Let me throw in one thing just to wrap up on that topic. Formal technology is actually already permeating its way into dynamic simulation, where rather than relying on pure random choices for generating sequences or scenarios, we're actually now, we meaning the industry, is starting to develop technology and using formal techniques to be able to generate intelligent sequences for dynamic application in a simulation or in an emulation environment. So it's not only is formal growing in terms of an application into and of itself, but it's growing and permeating into the dynamic simulation and emulation environments as well, although for generating intelligent sequences. So it is definitely coming.
Okay. Is there any questions in the audience? We have one online, but if there's any in the audience, we'll take that first. Okay, thank you. Good.
So if we reach that far in the future, talking like 10, 15 years, I have the feeling we assume that we stay with the design technology as we are at the moment, like writing RTL and so on. But if we reach that far in the future, maybe, then we maybe run software on a PC and don't need emulation. So what are you thinking about this?
I would tell you that the future is here. If you look at the 2 years ago, the AMBA 4, and look at AMBA 5, with the cache coherency extension, it is the original verification project of AMBA 4 2.5 years ago for the consistency of the internal specification and the consistency of the entire subsystem, including the cache coherency and the implementation verification, was all done with formal. There was no simulation. Simulation was done much later as a also process. So as the abstraction goes up, it's almost impossible, it will be impossible to capture the specification of a system like that in RTL. It's just too big, too complex, too implementation detail. As a matter of fact, many of the RTL generation will become automatic. But the formal methodology, formal meaning capture the spec in an executable way, prove it mathematically to be correct and internally consistent, this methodology is completely applicable, already used by advanced users. I'm not saying this is permeating 500 users. So the future is here. It's not going that way. How applicable is formal to software verification? Much more difficult problem. It started there, true, 30 years ago, 35 years ago, but it's a much more difficult problem. By the way, formal does know about timing in a different way, but it does understand timing. And it will understand software. I feel this is a safe prediction as predicting that the sun will rise tomorrow. It will understand software.
Yeah, I agree to what he was just saying. We are already there, so the challenges are there in raising the abstraction. We put microcontrollers on it, not caring about its details, put USB interfaces, all kinds of things to it. I would say the new challenges are coming more from the side of the analog arena. We heard from Mr. Rumondl this morning that analog will start getting into the picture, which makes things even more complex. The other dimension of complexity comes from low power design. Once, not perhaps everybody of you will be faced as of yet with that, so low power will make things much more complex. Hardware software co-verification is another discipline that will make things more complex, especially if you use off-the-shelf components, right? And that would really drive you. And come back to what JL was saying, time will be little, so you will have only a couple of months where you had, let's say, a year or two, 5 or 10 years ago, so that will make things really challenging. That's my view.
Okay, we have mostly discussed today about large digital designs, and there was only a small focus on the analog part from Martin this morning, and I believe the analog or analog mixed signal parts in designs will play a more and more important role, and this will not raise up the level, it puts it down, but it's really important, and because the world is analog and not digital. And this is what we have to consider, and we have to expand existing methodologies that we can drive and solve, say, the analog and analog mixed signal problems. This is my view. This is what my practical experience during the last few years was showing, that we have, especially in the automotive applications, we have a lot of interesting modeling topics, not issues, topics. And it's amazing what you need, say, in terms of creativity.
So to your question, I really think no matter how you enter the design, as long as the base component is a combinatorial logic feeding a sequential element, I think the methods we heard today will remain. If that changes, if we come to asynchronous designs, then I think it's a complete new game.
I answered the last question twice, so I'll pass it on this time to...
Nice move. Yes, I definitely also think that something is going to move there. In addition to just taking a lot of components off the shelves, even doing a little bit then your own way in RTL, and it's very low level. So, but I also don't really see a major issue with coping from it in the verification side. To just make the word easier for the design side, and also taking back to the analog parts. Also, that's something we also see a lot with our automotive customers, that they currently are mostly worried about the analog side and analog mixed signal side, and how to cope with that in the future.
So I guess the question was, what are design processes going to be 10, 15 years from now? That was approximately it, right?
To the previous quote from Mark from Mentor. So at the moment we are talking about how to handle the horse, so maybe we should talk about how to also think of how to go to a car.
Right. Okay, so there you go. So it's like the telephone game here. I'd forgotten the questions. No, but actually, so back at, I don't know if did any of you attend DVCon in February this past year? Maybe not. So at DVCon, I actually moderated a panel called it was the industry leader panel called The Road to 1 Million Design Starts. The premise of the panel was that what would we have to do in EDA to enable not just, I think we've got 6, 9, 10,000 ASIC starts per year. Maybe you guys know better than me. That was the number I had gotten. Maybe 80,000 FPGA starts. What would you have to do in your chip design methodology to actually increase that to 1 million design starts? So instead of having several like massively large designs like Intel's or other folks, instead of doing that, what if you could have 3-person design teams and they could make very small chips very easily without a 30-person team? If that was the premise of the panel was what would have to take place for that to be even possible, sort of like the App Store, right, for iPhone or something, right? Anybody could go, high school script kiddies go and they write their great chips and they send them off and they prototype them, and it's a whole different thing. So I think you'd have to decide what will it look like 10, 15 years from now, 20 years from now. Will we do more small designs or these just fewer big designs? It probably makes a big difference because for someone like Intel, they have a whole different requirement. It's massively different, I think. So you can go to the DVCon website and you can listen to the audio. So.
Thank you. I think we'll take... Oh, there's one more question.
Do you foresee any new metrics coming up in verification, or is it fine with the current metrics and then we increase the horsepower? Or maybe we can measure the closure better with the existing horsepower of the tools? It's just an idea.
Question. Okay.
Somebody want to take it? I can take it. Keep going. Yeah. The interesting thing about metrics is, I think, what you do with them. So the thing that I have that bothers me about the metrics that I see in verification teams is that people have these metrics and they track bugs and the functional coverage, and if you ask them how they define quality, they point you to the bug chart. But what does it mean? I mean, I don't know. So what? I see your bug chart. That's fantastic. What is it? Is it what you expected? Is the customer having a good result? So I don't know what new metrics exactly. I don't know that I'm that brilliant, but I do know that I have not always seen a good definition of what quality is, and then how does that get driven back into the engineering team?
Yeah, I think the challenge of metrics is one of those areas where we're all continuing to do development as well. There's been a lot of research into, again, metrics or coverage that is specification driven or intent driven versus structurally driven and implementation oriented, which types of metrics are automatically sort of implicitly derivable from, for example, your RTL code or from your design, which ones have to be have to have some degree of intelligence put to it by an engineer to interpret a specification. I think we'd all like to think that there's a nirvana out there somewhere where we can have an executable specification. So from a specification, we use maybe formal techniques to be able to automatically derive. Here's what needs to be done to verify the design. That's a big challenge right now. There's automation in the area in some areas, and then there's ease of use technologies being developed in others. And then again, as JL said, the maybe even the more important thing is figuring out now what do you do with that information once you have it.
Okay, we are mostly talking about the traditional semiconductor technology. In 5 or 10 years time range, we might have completely different chips based on optical processes, and I believe this will require a completely different consideration and maybe also a completely different matrix, because it's based on other physical features and capabilities. Maybe we will not switch completely in this time range to new chip technologies, but it will have, say, a certain importance at that time.
I don't know what it means, but I will share with you that in the last Jasper user group, there was a very interesting presentation by a early adopter of the formal technology from ARM, and he actually presented some matrices that he's using. And he uses all the traditional ones. He showed a bug chart, but the interesting thing that for them, what was important is how much earlier they found the bugs as opposed to how many they found. So whether the graph had a ramp like that or a ramp like that really meant something to them. I'm not trying to say that because of what we did there was better. I'm just elucidating the matrices he used. The other matrix, the other measurement that he used was the number of bugs. But there was one interesting measurement that I've never heard anywhere or any other time before that. And he was measuring the number and the frequency of line changes, code changes, and how many times his RTL and how often and where the RTL has changed. And, you can ask the question, so what? So I'm not sure. I'm not trying to advocate one or the other. But it was very interesting to see that it was very important to arrive at the stability as early as possible in the, not just the verification, but also the design. This particular group is using formal in the design process and in the verification process. So that's another measurement.
Okay. Okay.
There's a great, looking at the changes with the bug rate, there's a great paper from Google. They talk about looking at the heat map of your design and where the changes, so if you make changes to the design, which places do the changes most likely cause bugs? Means if you see that in this file over here I can make a change and there's almost never any bugs there, but in this file over here, whenever somebody touches it, there are 10 bugs come out. Then you know if you change this hot file, basically, you need to do code reviews and extra things. You can't just let that one go off by itself and have some guy randomly change it. So it's actually a really interesting, that's a nice point that you made. Those are some interesting kind of things you can do as well.
Just quickly on that, yeah, some of our customers, they call it code churn, so they measure code churn, maybe heat map. The other thing on the heat map is well, some people measure psychometric complexity to look at the complexity of the design that's being changed, which also indicates whether it's likely to be a bug in there or not. But you can measure the complexity based on nesting of decisions, that type of thing. Okay, we'll take this is the last question now, we'll do it quickly so we can go to the draw, and that's one online. The question is basically saying, so about 15 years ago, constrained random was quite a big innovation in our industry. Maybe 10 years ago, assertions was quite a big innovation in our industry. So what's the biggest innovation since assertions, and what's going to be the biggest innovation in the next 10 years? That's a hard one, maybe. Maybe that's a hard one. Come on, you must have one.
Yeah, well, I think that the people that are working on the next innovation are not going to share it. And if they do, it's unfortunate for them. I don't know. I really don't. So, obviously, I think we are overemphasizing the different methodology that will emerge in design. Yes, there might be optical chips, but silicon is here to stay for a long time. A long, 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 long time. It's not going away. So the design methodologies, the verification methodologies that we're working on today are going to serve us in the next 20 years. System Verilog is old. Vera and E are very old. VHDL is ancient. I know. I was one of the people who worked on it at the beginning. So, but it's still here, still usable, still, well, more than usable. Completely relevant. I think what's necessary for us to think about is how do we impact software. We have an EDA industry that is about $7 billion, serving a $300 billion semiconductor industry, but we are not really serving the software side very well. So as an industry, that's where I would say that's the call to action, not necessarily one company or another.
Okay, I think I would say a few words to what you said. I agree more or less completely what you said. No, yes. But say coming back to the software, we were starting 15 years ago with hardware software co-verification, and say the problem I see is and this might be the requirement for the tool providers, because it's a question of speed we have. Say for soft hardware software co-verification, the hardware simulation is always the bottleneck. It's too slow for a more or less extensive verification of software. This is what what we experienced 12 years ago, and I think it's still the same. It didn't change so much. And there might be something in the near future that we get better solutions on this. But
well, I'll answer with. I mean, Oz, you're right. We're all here working on next generation stuff, and some of it we're more ready to disclose, and some of it is still. It's not even. The technology is still in not form yet to take to market. But since constrained random testing was the one that the person asking the question brought up, I'll mention something that is actually available today in terms of. Although it's reasonably new out on the market, and it's what I was talking about before, using formal techniques to generate sequences rather than random techniques. There are at least two companies that are printed in the book that have announced technologies in this area, and I think there are others that have not quite announced. And we also know that there are some of you customers out there that have done development in this area as well. But back in the 1960s, IBM pioneered some technology in the area of using NFAs to generate tests for compiler verification in the software world. And it was largely deterministic, and it was very difficult to break that barrier from a deterministic world of compiler tests and software tests into the non-deterministic world of hardware verification. And we're starting to make those breakthroughs now. And we're seeing phenomenal results in using graph-based synthesis techniques, not design and logic synthesis, but scenario synthesis on the fly to generate just as many tests in terms of quantity as you would see using a traditional constrained random test technique. But we're getting to coverage and going beyond your original coverage goals by 2 orders of magnitude faster, more efficient. And so it's a technology that is a little bit closer to the executable specification. Think about when we had a pretty major, I guess prior to constrained random testing, one of the big innovations in our industry was moving from gate level design to RTL level design, where we would focus on design intent in RTL and then let automation take care of the implementation and give us some dials, power, speed, area, whatnot, and automate the actual creation of the implementation. And this technique of using graphs to describe, or NFAs to describe functionality and behavior is akin to that in the verification realm. So instead of you focusing on, or us focusing on the implementation of a scenario or of a sequence, let's just define the intent and let the tools automatically generate that. So that's actually something that's out there today. It's pretty new. People are using it and seeing great results, and it's continuing to grow. And I'm pretty confident you'll be seeing more about it in the near future. So,
I was just going to say, I hope people don't think that. I mean, everybody up here would like to have some great new innovations, but I hope that people in the audience don't think that you guys also can't be thinking of these things. I mean, if there's something that you want, you should go build it. I mean, we would like to build it and sell it to you. But I mean, there's no reason why you can't build it yourself. So if you've thought of some great ideas, so why not?
Well, maybe budget is a difference. Time and budget, I can think of 2 of these. But that's negative. I should be positive. Sorry, Joe. Okay, thank you very much to the panel. I'll keep you up because some of you are going to have to do the draw first. But we're going to say goodbye to the people on the webinar, I think, now. So thank you very much.